Carbon fiber reinforced polymers are a staple of high-performance engineering. In aerospace, where weight reduction is a primary design driver, large-scale composite components like this wing allow for structures that are light and exceptionally stiff. While carbon fiber is highly effective under tension, it performs differently under pressure. When squeezed longitudinally, the material's strength can drop by 40% compared to its tensile limit. This drop is caused by a failure mode known as fiber kinking. Instead of compressing evenly, the internal microstructure suddenly collapses into a localized hinge. Because this transition is nearly instantaneous and happens deep within the material, researchers have historically struggled to observe the exact sequence of the collapse. To bypass this, researchers are using in-situ X-ray computed tomography. By scanning the composite while it is under a compressive load, they can track the 3D movement of individual fibers as they approach the point of failure. Increasing the reliability of composite structures depends on understanding why this microscopic failure occurs and how it propagates through the material. At the microscopic level, a composite consists of two parts: stiff carbon fibers embedded in a relatively soft polymer matrix. During manufacturing, the fibers are never perfectly straight. They settle into the resin with inherent waviness, known as initial misalignment. When compressed, downward force follows these wavy paths, converting longitudinal load into lateral shear stress, pushing sideways against the polymer matrix. The matrix's role is to provide lateral support, preventing the fibers from buckling. As long as the resin stays intact, it keeps the fibers aligned and maintains the integrity of the structure. The strength of the entire composite is ultimately a race between the stiffness of the fibers and the ability of the matrix to withstand that internal shear stress. In these micrographs, as shear stress exceeds yield strength, matrix microcracks form. The resin tears, losing lateral support. Unanchored fibers tilt cooperatively, rotating from the vertical axis to form a localized microbuckle band. This sharp angular change marks the exact transition to structural failure. Finally, as the fibers reach their bending limit at the boundaries of this band, they fracture. The material snaps, completing the Kink-band. This cooperative folding is the final collapse of the material's internal geometry. Once a single Kink-band forms, it acts as a stress concentrator. It propagates through the microstructure like a diagonal fault line, causing total failure. While adding more material can increase the total load a part can carry, it doesn't change the underlying physics. Kinking is a stress-driven instability. Once the internal stress reaches a specific threshold, the fibers will buckle regardless of the total thickness. To design more efficient structures, engineers use representative volume element, or RVE, modeling. This allows them to digitally simulate fiber arrangements, matrix properties, and manufacturing defects. Researchers can test how these factors influence the kinking point, predicting failure before a single part is built. Whether designing deep-sea submersibles that must withstand massive external pressures or lighter spacecraft for orbit, engineering the next generation of composites requires mastering the physics of the microscopic kinking cascade.